Okay, to the next topic, which is diffraction. Well, it's really not a new topic, it's still interference. And the book defines it as interference is the interference between a few sources or just two sources. Diffraction would be the interference between many sources. Okay. So we'll start with single slit interference. Single slit interference. What happens is, if you take a slit, just one slit, and let that slit width be A. This is the slit width, it's A. And you shine light on it. Right? Shine light on it. And you would expect what? What would you expect? What would you see on the screen? You should see light. So let's say the light is maybe blue. You'd expect to see blue only here, right? Just to the width. But that's not what happens. What happens is this. It will be blue a little bit, it will spread out. It will be blue all the way here. And then it becomes dark. There will be one dark spot here, dark spot. And then it becomes blue again, if I'm using blue light. So you see a bright spot, a central bright spot, and then bright, and then bright, and then it would get dark again. And then it becomes bright, and then it becomes dark, and then it goes on, in principle forever, but you can only see maybe the third or fourth one. Okay? And the question is, why does this happen, and how does it happen? Okay? Why does it happen, and how does it happen? So to explain that, we will explain it in terms of interference. It will seem arbitrary what we're doing. When we do the intensity of interference, the intensity of the diffraction, it will confirm our results. Okay? So how does this happen, and how do we explain it? So here's how we go about doing it. Again, the slit is so small. It's next week you will do a lab, and the slit width will be 0.02 millimeters. Okay, and then you will have 0.04, 0.08, 0.16 millimeters. So you're talking about a tenth to a hundredth of a millimeter. So very small. So here's the slit. Light is coming in. The way we look at it is this. Right, so this is the slit, light is coming in. Still a single slit. So the way we can explain it is this. We will think of the slit as maybe kind of, let's draw a virtual or like an imaginary line through it. And let's look at a light ray that comes in from here, and another light ray that comes in. This one is right below the top slit, and this one is right below this imaginary line that I'm drawing. Okay? And I would like to know at what point we would have destructive interference. Let's see. So let's look, let me draw this with blue. Let's say this angle here. The angle is theta. And let's say the angle is theta. And this one travels a little bit more, right? By how much? Remember, the slit width is A. So this is A over 2, right? And this is A over 2. So A over 2 sine theta, yes. So the path difference is, it used to be D. We used to call this D, but now it's, we don't have a double slit, we have a single slit. So it's A over 2 times the sine of theta. And by the way, if you're wondering, we don't have just two light rays. We have one right below this one. All right, let me draw this one. One right below this one and one right below this one. Let me draw the line from here to here. do you agree that the path difference is still A over 2 sine theta? And then you can do the one below this one and the one below this one, and then keep going until you get the one right above here and the one right above here. All of them have a path difference of about A over 2 sine theta. So the path difference is A over 2 sine theta, and this equals to, I would like it to be destructive, so I would have half a wavelength shift. Half a wavelength. I'm looking for the first one. So half a wavelength shift. So what do I conclude then? I conclude that A sine theta is equal to what? Lambda. Okay. A sine theta is equal to lambda. Okay. We'll do 3 of them, and then you will get the pattern. Here is the single slit again. Here's the single slit again. And now I'm going to divide it into 4 virtual, I will draw 4 imaginary lines. So here is one. Here's another one. So I'm dividing the slit into 4 spots, 4 equal slits. So what's the distance from here to here? A over 4, yes. And this is A over 4, A over 4, A over 4, right? Now let's look at, again, let me draw a ray that's right below and a ray right below this line. And now ask, what's the path difference between this one and this one? What's the path difference?
A over 4 sine theta.
A over 4 sine theta. And let me ask the following, the next question. What is the path difference between, okay? So yeah, we said A over 4 sine theta. Let me draw it right here, in here. I have A over 4 sine theta. I'll put the equal in a moment. How about for this one? The one here and the one right below this line, the one right below this line. And I'm interested in what their path difference is. It's still A over 4 sine theta. Right? We're talking about a small angle. You might think this angle is a little steeper than this, but again, remember the screen is a meter or so away, and this one is a fraction of a millimeter. So the angle is still the same. And what's the advantage? So look at this. Every 2 dots that, as I keep going this way, they are shifted by A over 4. And then the same thing here. Every 2 dots here throughout, they're shifted by A over 4. So adding them together, and I want destructive interference. So I want lambda over 2, and this will give me A sine theta equals to what in this case? If I solve
2 lambda.
2 lambda, yeah, thank you. 2 lambda. The first one gave me 1 lambda, this one is giving me 2 lambda. Let's do the third and last one, and then hopefully we get the pattern. I'm going to now divide this into 6 different slits. So here is, I made my slit a little bigger now to be able to tell. Here is the screen. So that's a 1/6, right? Each of them is 1/6. So A over 6, A over 6, A over 6. We have another A over 6, A over 6, right? All of them. So let's draw one right below here, one right below here. Maybe my screen needs to go higher. What is the path difference here? A over 6 sine theta. Equals to lambda over 2, and that tells me then A sine theta is equal to 3 lambda. 3 lambda. By the way, there are the ones below also. I should have included down plus or minus 1 lambda, plus or minus 2 lambda. Because if we looked below, we would have found those also. And this one should have been plus or minus 3 lambda. So what do we get for the general rule will be what? A sine theta equals to what?
M lambda.
M lambda. And what is M? What's M?
Integer.
An integer, which one? Does it include 0?
Yes.
Would it? If we have 0, that would be constructive. Right? In the middle, it's going to be a bright spot, not going to be dark. Remember in the middle here? It's going to be bright. It's only dark here, here. So it's only, let me start. Here is 1, here is minus 1. Here is 2, here is minus 2. So it's going to be this, all the non-zero integers. Okay. And what does this tell us? The location of the bright or dark spots? Dark, destructive, yeah. So this is the location. Destructive interference. We'll do an example and then we'll talk about the intensity of this interference. It says here, let me write down the problem so that we get used to the words. You pass 633 nanometer laser, so you pass. Should I write the whole thing? Sorry, let me just write parts of it. So lambda is 633 nanometers. So you pass 633 nanometer laser through a narrow slit and observe a diffraction pattern on a screen 6 meters away. So here's the slit. The slit width is A, and we observe on a screen that is 6 meters away. So L is equal to 6 meters, right? So 6 meters away. Again, this one is like a fraction of a millimeter, and this one is 6 meters away. So it's very far away. So the angles would be very small. So all the approximations we mentioned are still are good. Okay. It says the distance on the screen between the centers of the first minima on the side of the central bright fringe is 32 millimeters. So the central bright fringe. What is the central bright fringe? All this is going to be bright. So here it is. So that's the middle. But remember, it spreads out a little bit. It's going to be, all of this is going to be bright. But then we'll have dark spots here and dark spots here. This one is known as m equal to 1, and this one is m equal to what? Minus 1, yes. And we're told what the distance between here and here. We're told it is 32 millimeters. 32 millimeters. Okay. And the question is, how wide is the slit? This slit, how wide is it? What's A? Right? Any ideas how to answer this? We use this? Yeah, we use this. So let me draw a line here through the center of the slit. here. This will be theta, right? This is theta. And let's call this distance from here to here y. This distance to be y. So we know, I'm looking for, m should be 1 here, right? For this one, it's 1. So I know this. We have m is equal to 1, and so I have a sine theta is equal to just lambda, 1 lambda. And so sine theta is almost equal to tangent theta, right? And tangent theta is y divided by L. So theta is small, so sine theta is almost equal to tangent of theta, which is equal to y divided by L. And so I get a times y divided by L is equal to lambda, and that means a is equal to lambda times L divided by y, and we plug in the numbers. 633 for lambda, or 6.33 times 10 to the minus 7. 6 meters per L. And how big is y?
16.
16 millimeters, right? Yeah. So 16 millimeters, so 16 times 10 to the minus 3 to make it into meters. And so this turns out to be 2.4 times 10 to the minus 4 meters, which is 0.24 millimeters. Next one is, I should ask before, any questions on this?
If we only did like the one part of y, would we not multiply it times 2 to get the size of the slit?
So the size of the slit is A, regardless whether I, yeah, so this is A, just the size of the slit. Yeah.
Well, because I was thinking, like, you solve for the top part, don't we solve it, like, for the bottom part, and then.
Not quite, yeah. Yeah, so this A is just the width of the slit, regardless of what M is or what theta is. So this one will stay to be the width of the slit.
Okay.
Yeah. I think what you're thinking is this thing here, yeah, that's twice, that's 32, yeah. So let's do the intensity, right? Let's do the intensity.